Welcome to this talk about spiking neural network decision feedback equalization. This work was carried out together with Alexander von Bank and Laurent Schmalen, and it was presented on the conference on System Communication and Coding 2023 in Braunschweig. So, as a scenario what we often see in the real world is that in communications we experience a multipath channel. Therefore, at the receiver, equalization is needed, which you can see down here. So we want to transmit a signal, ST. We experience a multipath channel, HT, and then we of course get some random white noise added, and then we receive our signal and we need to equalize it in order to get back the data which we transmit. In the past years, machine learning has shown that it can improve the equalization performance. However, there's a trade-off between computational complexity of the machine learning model and the performance of the machine learning model. State-of-the-art equalizers are mostly fully digital. So if we think of the current neural networks, so they ran on a GPU or TPU, so they are fully digital. However, if we take a look at this graph, we see on the y-axis the efficiency, so the giga, multiply and accumulate operations, which we can execute per joule, and we see that digital electronics are limited in the amount of operations they can do per joule. However, if we take a look at neuromorphic electronics, they can do a lot more, so they are more energy efficient because they can do more operation per joule. So our question is, can we implement an equalizer for neuromorphic hardware? Therefore, as just introduced, we created a small problem setup. So we have a random bit sequence, BK, which we map to complex symbols, XK. Then we experience a frequency selective channel. We add some additive white Gaussian noise, and then we want to equalize using neuromorphic hardware and want to demap the found symbols to the bit stream, so we can estimate the transmit bit stream. As neuromorphic hardware, we use spiking neural networks, which can be run on neuromorphic hardware, and they show to be promising candidates to be run on neuromorphic hardware, and they enable energy efficient computing. What are spiking neural networks? So spiking neural networks are networks of interconnected neurons with adjustable, so trainable weights, and they mimic the behavior of the human brain more closely than traditional artificial neural networks. So how do they do that? The neurons don't exchange information in real numbers like traditional neural networks. However, they exchange information via discrete events, so 0 or 1, the so-called spikes. So they fire and then they relax, and then there's no energy needed for that. Let's take a look into a neuron's dynamic. So a neuron exists of internal state, Vt, the so-called membrane potential, and then we have some input spikes, which you can see here. Those are the purple dots, and the input spikes induce a synaptic current. The synaptic current charges the neuron state, so the membrane potential, over time, and as soon as a spike threshold is reached, so as soon as the membrane potential, the state, reaches a spike threshold and exceeds it, output spike is fired and the neuron is reset, which you can see over here with the heaviside function. So as soon as Vt gets higher than the threshold, then output spike, the blue dot, is generated and the neuron is reset. Just brought an example along over time. So on the x-axis you have the time, and then you see the purple dots again, like in the example before. That's just the behavior inside of one neuron, and as you can see, each purple dot, each input spike induces a synaptic current, so that's the yellow line, and synaptic current results in an increase of the membrane potential, so the state, that's the green line over here, and the red dashed line, which you can see, that's the threshold. And as you can see, the first 3 input spikes aren't dense enough in time that the threshold is exceeded. However, the last 3 spikes, they are so dense in time that they sufficiently charge the neuron state and the threshold is exceeded, and therefore the output spike, so the blue dot, is fired. One question is, since we talked about spikes now, so we put spike neural networks, process spikes, so we somehow need to encode the information, the received symbols Y element C, into spike signals. So somehow we need to find this orange block where we have the Y, and then we get some spike signals out. In this work, in this presentation, we want to propose ternary encoding. So we assume that the value we want to encode, so Y is limited to minus Y max and plus Y max, so it's centered around 0, and then we want to encode into ternary spikes. So we have a -1 or 0 and a +1, so we can do nothing, or we can charge a neuron, or we can discharge a neuron with our spikes. And how do we do that? We use the quantizer, M-bit uniform quantizer, and we just take our signal Y, we take in the upper branch the absolute of it, then we quantize it, and then we have the spike generator, which just puts the different quantization bits. So if we have M quantization bits, we get out M spike signals, and the spike signals are just described by if the quantization bit is 0 or 1. And to get the -1, we just take the signum function of the Y, and then we just multiply it with it. So if we have a negative value for Y, we'll only get -1 as output signals, and if we have a positive value, we just get the quantized value of Y with 0s and 1. So how does our setup look like now? As just said, we have YK, which is our received symbol after the frequency selective channel, AWGN channel, and then we apply the ternary encoding, and then we put these signals into the neuromorphic equalizer and demapper to estimate the transmit bit sequence. So we propose now to use a decision feedback equalization structure. So as you may know, a decision feedback equalizer decides for transmit symbol and then feeds back his decision. So that's why it's a decision feedback structure. And over here you can see we have the YK, we do a ternary encoding, then the forward path has n taps, so we delay the incoming symbols up to n taps. In the backward path we have m taps where we feed back our decision and delay it up to m taps. And so the equalizer at all has n plus m taps. And as you can see, we feed into our SNN, which is the main part of the equalizer. We feed into the SNN the last incoming symbols. So that's the upper branch over here, and the lower branch, those are the m last decisions. And in the SNN we apply the argmax, and then we estimate the class, and with the bitmapper we can demap. So why applying argmax? Let me talk about the symbol decision. So in the SNN output layer, as we just discussed 2 slides before, the neurons, they develop over time. So depending on incoming spikes, they get charged or discharged in the voltage. So in the output layer, we just said we set the threshold that high that we do not generate spikes. And then we run our SNN for Tmax. And the output layer, here as an example, we have 4 output neurons, which means we can classify 4 different classes. We just say, okay, so each neuron represents 1 class, and depending on how the voltage of the output neuron develops, we classify this class. So if the voltage gets really, really high, then it will be our class. If it gets rather low, the probability that this is the class we classify for is rather low. So as you can see here in this example, we have those 4 classes and the argmax. So we'll just after Tmax, we'll read out the voltages. So we have the values over here, which you can see, and the argmax in this case will decide for the second class, so the green line, because the green line has the highest voltage after the SNN is run for a certain amount of time. To show our results, we used the well-known Proc channels A, B, and C, and the model, of course, we already discussed, and just to get it back into mind, we have plotted the different channels over here. So Proc is A, that's a rather nice one. B is a little bit harder, and C, yeah, that channel is already a bad one, so there's a lot to do for equalization. So in our simulation setup, we know that our input neurons in our SNN are given by the number of decisions we feed back, so M times N out. N out is the number of classes we have, and in the input we need to, since yk is a complex value, we split it into a real part and an imaginary part, so that's the 2 in the N times 2 times M, and then we have M quantization bits, so ternary encoding uses per value M signals, so we need M input neurons for that, and we do that N times, since the upper branch, if you remember in the SNN, DFE had fed into the SNN N times the last received symbols. And for all equalizers we use N-tab is 31, and in the SNN architecture for the A and C channel, which we will introduce now, is as follows, or as you can see. And for the A channel we use a 16 QAM, and for the C channel we use a QPSK modulation. In all simulations for the encoding, ternary encoding, we used 8, so M equals 8, so 8 quantization bits, so 1 real or imaginary value is mapped to 8 spike signals, and we implemented everything using NOS. And the training parameters for all machine learning models was 10,000 epochs with a batch size of 200, and we learned with a learning rate of 10 to the power of -3 with cross entropy loss. To benchmark against well-known equalizers, we furthermore calculated the minimum mean square error equalizer, the decision feedback equalizer, and the optimal maximum a posteriori detector. And furthermore, we benchmark against artificial neural network-based approaches. So we just have the same structure as before, we just replace the SNN by an ANN, and one time without encoding and one time with encoding, so that we can spot the impact of the ternary encoding later. Furthermore, in another paper there was log scale encoding as a possible encoding proposed, so we will investigate the log scale encoding of this paper too. And as already stated, all equalizers use 31 taps. So let's talk about the C channel, so the hardest channel over here. So as you can see, the maximum a posteriori equalizer as the optimal equalizer performed best. Then the DFE is the second best, and linear equalizers like the minimum mean square error, they perform worse. Let's zoom in a little bit and let's add the artificial neural networks. So ANN trained at 16 dB with and without encoding. As we can see here on the green dashed line, which is the encoded line, we already see that we have some losses introduced by the encoding. Now add the SNN DFE, so one time with the log scale encoding and one time without a log scale. So the dashed orange line is with the log scale encoding and the solid orange line is with the ternary encoding. Here we can see that our proposed encoding, so the ternary encoding, seems to be more robust than log scale encoding, at least for our case and the channels we trained for and the model we trained for. And now we can even compare different SNNs trained at different SNRs. So we have in purple SNN trained at 15 dB, in blue SNN trained at 16 dB, and in yellow SNN trained at 17 dB. And as you can see, SNNs are able to generalize over the whole range of EB to N0, and furthermore, a proper choice of EB to N0 for training is more crucial than training an SNN at each EB to N0. So in this case, we can see over here that with the purple line, so the SNN trained at the EB to N0 of 15, we're close to DFE performance. We still have a small gap, but we're close to it. So just to show another channel, so the A channel with the 16 QAM, for that channel the maximum a posteriori isn't feasible anymore. And as we can see over here with the SNN trained at a B to N0 of 13 dB, we are able to roughly get decision feedback equalizer performance. So what are takeaways from this talk? So first of all, we contributed ternary encoding. So as we have seen, the encoding for the artificial neural network encoding introduced some losses, so the resolution is limited by M-bit quantizer. However, we've shown that it's more robust than log-scale encoding, which we have taken from another paper. And the SNN DFA with ternary encoding gets similar performance as the decision feedback equalizer and ANN-based solutions. However, we have the promise of energy-efficient computing as soon as neuromorphic hardware gets commercially available. So as an outlook, we are searching for better learning tools for SNNs, so that's still an open topic and hot discussion in the neuromorphic community, how to train SNNs properly. And we think that it's a promising technology for the implementation of future receivers due to the promise of energy-efficient computing. So thank you very much for your attention. If you have questions, you can put it in the comments below. We just want to thank you, everybody who sponsored this work.